some of your some of yours homework that I have assigned to you, question 4, 5, and 6. I noticed some of your solution. I mean, I haven't reviewed everything yet, but some of the solution provided by you, some of you, for question 4, I think there is misunderstanding towards the solution. I mean, towards what you need to do. So I will discuss now. Uh, the solution for question 4 first. So for question 4, uh, find the electric field at a point P. Find the electric field at a point P above the square loop. Above a square loop, yeah, a loop, yeah, not a flat plane. I mean, not a piece of uh, rectangular sheet. A square loop, that means it's a loop but shaped in rectangular. I think one of you, I think it's Kai. Sorry, some of you asked me a question. Yeah, Kai Boon. So you are asking me about. You say you don't understand the question. So now I wanted to tell you that it's a loop. Okay, it is a loop. Each of the side is a rectangular loop. Sorry, it's a square loop. Sorry. So each of the side here, the length of the loop is a. Yeah. So each of the edge length of the square loop is a. So uh, if let's say the loop here carry a uniform line charge of lambda, carry so carrying uniform line charge of lambda. So each of these arm here, each of this length here of length a, they have a charge density, a line charge density of lambda. Okay, a line charge density of lambda. Okay, so now I'm going to provide you the solution. So again, please see carefully and compare to your solution. Some of you please compare to the solution that you have provided. So as I said, there is some error in your solution. Basically is mainly due to understanding. All right. Okay. So So question 4 here. So what you can do here is, assuming that at the center of the rectangle of the center of the square loop, it is the origin point, the point of origin. So since we have identical length, so what we are going to do is we are only going to take one length at a time. That means we only have to evaluate. We only have to evaluate the electric field contributed by one of this length, and then eventually we will multiply everything by 4. Okay, so now, so say that, let's say this is sorry. So say that this is the origin, point of origin, and let me add an axis. Okay, so I have draw another axis, just I mean, for illustration purposes. Okay, say that this axis here represent y, okay, or x, up to you. Let's say represent y, this axis here, and I would say this axis here represent the z-axis. Okay, so now when every time I approach the problem using Coulomb's law, I'm applying Coulomb's law. So by using a point charge concept, so as I said, use infinitesimal length along, let's say I will concentrate on this one length first, okay, I will concentrate on this length first, only on this length, okay, this length here, okay. So I put a blue mark. So so say that there's a point charge here, contribute an electric field at point P. Okay? Contribute an electric field at point P. So this point charge contribute an electric field of dE, yeah, because it is infinitesimal. So so this infinitesimal point charge will contribute an electric field at point P. So the electric field here is dE. So it's a small differential electric field. Okay. So the height of point P, is given as Z. The height of point P is given as Z. And here we have, let's say, so here, let's say I mean, I'm not sure you can see this properly. Let me just redraw this again. sorry, just let me redraw this again. So okay, can you see the triangle that I draw here? Everyone, can you see the triangle that I draw here?
Can.
Okay. So the green line represent the direction of the electric field contributed by a point charge here. So I will put a green dot here just to represent the point charge. So the point charge here dq, the point charge here dq is represented by lambda times the infinite signal length, which is dl. Yeah. However, our dl here will be represented by dx, because now, I mean, for this length here, for this length here, it is oriented along the x-axis. Yeah. So it's oriented along the x-axis. So it is therefore the variable of interest. The variable of interest, it is dx. Okay. So assuming that here to here, so this length here that I highlighted in red, the length here is arbitrarily is x. Yeah. Okay. Arbitrarily is x. And here to here is a over 2. So it's a over 2. So therefore, this line here is, let's say, a small r. I will represent this as a small r. And for the green line, as capital R. Okay. So for small r in vector form, so small r is equals to a over 2 y cap plus x cap. Yeah. And therefore, capital R, so the vector represented by the green line, okay, by the green line, represented by the green line, it is therefore z cap minus r cap. Sorry, vector r, right? However, so here I can write z cap minus x cap plus a over 2 y cap. Okay, so this is the vector that we have established for a point charge that contribute an electric field at point P. So this is the vector for this point charge here. So this point charge here is arbitrary. As I have mentioned many times, you can choose any point along, this line here. So, but however, eventually, the formulation of the problem, it is still based on our declaration or our definition of this vector here. Okay, so now, so E, dE, so vector, the electric field is the integration of dE which is rho L lambda dx so it's actually dq first. So using Coulomb's law, so r squared, right? R cubed r to the power 3 over 2 vector r. So this equals to, so dq here is lambda dx, right? So it's lambda dx so this is z square plus x square plus a over 2, sorry, so x square plus, sorry, my mistake again, sorry, x plus a over 2 square, sorry, raised to the power 3 over 2, and the vector here is z cap minus x cap plus a over 2 y cap. Okay, I have also mentioned before that if with reference to this point P here, if we observe carefully, it is actually the square loop provides some kind of symmetry, right? Provides some kind of symmetry, so that if we take into account of this point charge here, right, and the other point charge here, and opposite point charge at this at the same rectangle, okay, and another point charge here that contribute the same dE. So we can say that it contribute the same the same dE here because that the line charge density lambda is uniform. So we can say that, right? Unless lambda, the line charge density is non-uniform, then we can't do that. So since this line charge here is uniform, okay, so therefore I can say, okay, another point charge here which is opposite here, let's say. So if you can see my drawing, so contribute an electric field here. So I do not have to elaborate further since I have mentioned the symmetry property. So another line chart here, so that you will cancel out the what they call that. What they call it? What I said previously. So you will cancel out horizontal field or vertical field.
Horizontal.
Sorry, vertical field. Horizontal or vertical field?
Horizontal.
Okay. So, in other words, I do not have to take into account of the x cap component and y cap component, right? So if let's say we exploit the symmetry property, then we do not have to take into account of the x component and y component, and therefore by exploiting the symmetry property of the square loop, the symmetry property of the charge density of the square loop of the square loop. So this implies now the electric field E reduces to okay, so reduces to only the Z component, right? Okay. So the formulation of a problem is now complete. So this only leaves us the integration part, right? This only leaves us the integration part. So I have demonstrated to you before how we deal with this. Okay, how we deal with this. So we can say, so now we only have one thing to consider, which is the integration variable now is dx. So the integration variable is x along x-axis, right? So the rest of the rest of the term can be considered a constant, and therefore we can factor out outside the integral. You can factor out outside the integral. So by variable substitution, So we can use so by variable substitution, what we can use? So we can use x plus a over 2 equals to z tangent theta, right? Therefore, dx is z secant square theta d theta, right? Okay, so we are going to use this variable, substitute as x plus a over 2, the whole variable as z tangent theta. So therefore now, theta, so this x plus a over 2 over z and square root of z squared x plus a over 2 whole thing square. So recognizing this form here, so directly we can reduce the integration as cos theta d theta. So now, so it's lambda z over 4 pi epsilon naught sine theta, right? The integration of sine theta, the integration of cos theta becomes sine theta. So from negative a over 2 to a over 2. So since if we look back at the diagram here, since O is the origin, and therefore this point here, at this edge here, at these vertices is negative a over 2, and the other vertices will be a over 2. So therefore the integration limit is from negative a over 2 to positive a over 2. Okay, guys, give me a second here. I just want to check my working again. 1 over z square. Okay, yeah, I just want to check. Thanks, Kaigun. I just want to check again. Okay, so now, uh, so finally, by substituting the limit, so we have lambda 4 pi epsilon naught z square. So it's going to be a over square root of uh, z square plus a square. Okay. And this is only for one length, right? So just now I said the total will be, therefore the total contribution uh, of of the electric field so total contribution electric field by the square loop it is then equals to 4 times so E net 4 times E. So this is lambda over pi epsilon naught z square plus a square in the direction of z, Okay. Okay, the answer is slightly different. Wait, I might have done something. Just give me a second. Just let me double check the formulation again. Sorry. Ah, okay. Sorry. I think I know what I did wrong here. Uh, yeah. Sorry. It is this. This is the problem. Sorry. It's supposed to be x square plus a square over 4. Sorry. Yeah, because uh, the magnitude of r. Okay. So for magnitude of r, I should square every component, right? So just now earlier I write it wrongly. So sorry about that. So this also. Three to the power of 2. So this is. So now our substitution will be slightly different. Our substitution will be slightly different now. Okay. Sorry. I just need to remove this. Sorry about it. I will rewrite this again. I mean the same statement. So the correction is, as I said just now, I did wrongly for the magnitude of R. Yeah. So initially I wrote this way. Initially I wrote magnitude of R as Z squared plus AO2 square. Yeah. So this is wrong. Sorry about that. I just mislooked on this. Okay. So this is wrong. Yeah. Okay. So after substituting the limit, after substitution of the limit of x for, I mean the integration limit for x, it is therefore lambda z times, okay, so it is a over square root of z squared plus a squared over 4. Sorry, a squared over 2, not a squared over 4, sorry. A squared over 2, yeah. Okay, so that's the final answer. So the electric field, this electric field here, bear in mind, it is only contributed by 1 amp. So I put a remark here, electric field only contributed by 1 amp. By one length or arm. Okay. So the entire expression of this is only contributed by 1 arm. So now, therefore, the net contribution of the electric field at P by the square loop so is lambda z, so is pi epsilon naught So this is the final answer then. Okay. Okay, so my apologies to the earlier mistake on the vector r. Okay. So now it should be correct now. I mean, this is what we this is what we derive, which is the same as provided by the answer in the tutorial. Okay, we have a little bit more time. So far I presented the solution. I mean, just now I mentioned that some of you did something. I mean, as I said, the solution that I some of you did something which is not right. So, for example, I saw some of you, what you did here is you dq, okay, which is lambda dl, and which is also you put lambda dx, okay. Then you integrate both sides. You integrate both sides, and you get q, which is lambda times a, yeah, which is a length. And then eventually, what you do is you substitute into lambda a over something like this, lambda a 4 pi epsilon naught, and then you calculate some vector r here. And okay, this vector r, and instead this vector r here, what you did, I'll just draw back the diagram. So this is one of the length. You take it at this center point. You take it as this center point, and then this is your r. You calculate this length here. So this is z, this is a over 2. And then you substitute this r here as square root of z squared plus a squared over 2, a squared over 4, okay? Yeah, so what's wrong with that is, first, you find the entire, you find the entire charge of the length, and then you assume that this charge here is concentrated at this point and contributed the electric field at this point. So which is not right. I mean, do you see the error? I mean, do you see the error in the understanding here? I mean, I don't know who, but I saw a few of you who did this. So obviously, this point doesn't represent typical mistake. I would put here typical mistake. Okay. So this point, it is assumed as Q, which is wrong. Which is wrong. Do you understand why I'm trying to explain it here? I mean, for those of you who did this, can you please refer back? I mean, refer back to your solution and try to compare what I have explained to you. And this is the typical mistake here. Guys, are you with me, guys? Yes, Muhammad Adin. Um, I'm talking now about this solution now. Okay. So when you do this, so you're assuming that the entire, now you put Q, which is, I mean, you calculate the entire charge of the line first. And then you substitute this as Q divided by 4 pi epsilon naught R squared, which is a point charge. But this is a line charge. You can't assume that this is a point charge. The entire charge here is concentrated at this point. You get what I'm saying, Muhammad Adin?
Yes, yes.
Sorry? Yeah, you can, yes, you have to assume an arbitrary point. Correct. Therefore, if you look at my formulation of the problem, if you look at my formulation of the problem, so this point here, this point here, which is arbitrary, okay? And when I say arbitrary, that means that this point charge here is I mean, we have to include all the contribution of each point, or the contribution of each point along the line charge, right? So therefore you have to integrate along this line when we try to evaluate the electric field. So on the other hand, if you do it this way, okay, if you do it this way, first you take dq at one of the point, and then you integrate the entire length and get the total charge. So what you actually did here is you find the total charge of the line. Okay, you find the total charge of a line of one of the arm. Okay, I should say one of the arm. And then the second part here, what you did here is you directly substitute Q. And we knew that this electric field, I mean, by looking at the expression, this is supposed to be a point charge, right? This is supposed to be a point charge calculation. If we have a point charge, yes, we can calculate an electric field at a point. And eventually, along this line, what you did again is you put a point charge here. I mean, you assume that the total charge that you find, you put it this way, and then you calculate this Q. I mean, the contribution of the electric field at this point. So therefore, the rest of the, the formulation of the problem is not correct. If you're able to understand what I have demonstrate to you today for the solution of question 4, and as well as the previous the previous example in the notes. If you follow through, and if you look back at your own solution, you find that this is a bit contradictory, right? I mean, think about it. I want you to have a thought on this. So this is a typical mistake. I mean, not only that you have, I have seen typical mistake like this. Yeah. So you shouldn't find the total charge of the entire line and then assume that the total charge is concentrated at this point here. So which is wrong, right? Because the total charge, it is distributed along it is distributed uniformly along the line. So you cannot just you cannot just assume that this is Q. So you get what I'm saying, everyone? Yeah, Kaibun. The formulation, it must be arbitrary along the line charge, and therefore the process or the solution obtaining the answer, we have to consider the integration along the line charge. So we cannot calculate a single point. We cannot calculate the total charge of the line and then put it at a point on the line charge, because as I said, the line charge, what you found earlier, what I have demonstrated earlier in the solution is that the wrong solution here. So what is that? You find the total charge Q, which is lambda times A. This is correct. I'm not saying this is not correct, but the process of obtaining the correct solution is not correct. It's not right. Because eventually, if you think that this charge here, it is at here, is wrong, because the charge distribution Q, it is distributed for the entire line. It is not at this point. So everyone, do you get me? Guys, is it okay?
Yes, okay.
What about others?
So you can scroll down.
Need to scroll down, scroll down.
Scroll down, sorry.
The chat box.
Okay, sorry. All right. Can't assume at mean line since not infinite. No, you can't. All right. Okay. So I hope everyone, get what I tried to explain. So I will reply back I will return back your homework by this week, hopefully. Okay. So I will pinpoint where is your mistake, so that you know, so that you don't repeat the mistake again. All right, I will see you at the other Google Meet. Yeah. Thank you, everyone.